I wanted to work through an example that involves applying Kirchhoffs rules for electrical circuits to the particular electrical circuit of a RC circuit for charging up a capacitor. That circuit's pictured in the figure here in the center of the whiteboard. That circuit has a switch, a battery on the lower arm of the circuit and a resistor and a capacitor on the upper arm of the circuit. We're going to imagine at time zero, t equals 0, we close the switch, completing the circuit at that moment. And we're going to imagine the current that flows around the circuit, the voltages that appear on the circuit after we've closed the switch. We're going to consider the current and the voltages based on Kirchhoff's current voltage rules. So this is a simple circuit for application of Kirchhoff's rules in one sense. It's a simple circuit because it doesn't have any nodes or junctions. It's just a single loop. It's a more complicated circuit in another sense because this is a circuit in which there's not a steady state current, not a constant continuous current, but this is a circuit in which there's a momentary, a fleeting current. The time scale of the current is the time scale of the RC circuit. It's the time scale determined by the capacitance of the capacitor and the resistance of the resistor. So those two features make it different from examples of Kirchhoff's rules in resistor circuits where you have nodes, you have junctions, but you don't have capacitors. So you have a steady state current rather than a time varying current. In this example, we're going to start with Kirchhoff's current rule. And Kirchhoff's current rule for a single loop is essentially that the current through each component in that loop, the capacitor, the resistor, the switch, the battery, are the same. Kirchhoff's current rule at its core is the conservation of charge. And for a single loop, the current must be the same through each of the components, the capacitor, the resistance, the switch, the battery, in order to conserve charge. So we're going to start with Kirchhoff's current rule, and we're going to write down the current that is flowing through the capacitor and flowing through the resistor, flowing through all components of the circuit. We'll then move on to Kirchhoff's voltage rule, apply that voltage rule to this single loop. The voltage rule applied to this single loop says if you start at some location in the loop and you walk around the loop, you're going to incur ups and downs, hills and valleys in electrical potential. But if you sum up the elevations and the drops, the total change in potential, if you walk around this entire loop, will be 0. So some increases in potential, some decreases in potential, but they must add up to 0. That's Kirchhoff's voltage rule applied to this circuit. We'll discover that that rule tells us how the voltages on the capacitor and the resistor appear in the circuit and how they're related in this particular circuit as we charge up the capacitor through the resistor. Here I've written it down on the left for the capacitor. It's the current passing through this leg of the circuit. And here's the current for the resistor. That's the current in this leg of the circuit. As I said, the current through all the components in the circuit are the same. So the equation for the currents here are the same equations. They're the same currents passing through the capacitor and the resistor. Notice that I wrote the current as a lowercase I in each case. I'm using that to refer to a time varying current. Notice also that I put clearly in parentheses that it's a function of time, just to make that really clear. Over on the right-hand side of the equation, I've got I naught times a function of time. It's an exponential function where the exponent is a negative exponent, and the exponent involves the ratio of the time, the variable, to a parameter that's the time constant, which is equal to RC. So this equation describes the current around the circuit. The current is greatest at time zero, the moment you close the switch. That's when the exponential with the negative exponent is greatest. It's 1 at that moment. The current then shrinks as the time increases. As the exponent becomes larger and larger, it's negative, larger and larger in a negative direction, the exponential function shrinks. And if we waited long enough, if we waited for times of many time constants, that exponential function would be essentially zero. So it's telling us that after a long time compared to the time constant, there will be no longer any current flowing. The I naught, that's the current that flows the moment the switch is shut. So that's the current, initial current, and that current flows at time zero, and then that current starts shrinking and shrinking and shrinking according to the exponential. What about the voltages, corresponding voltages for the capacitor on the left and the resistor on the right? Can we write those down? But yeah, we can write down those voltages using Kirchoffs rules, using the voltage rule. The key thing is that in this circuit, in addition to the capacitor and the resistor, and ignoring the switch when the switch is closed, because it's really not a circuit component then, there's a battery. And that battery is providing a fixed voltage, a fixed electromotive force to the circuit. Kirchhoff's current rule then says that that EMF is shared between the resistor and the capacitor. And really our only job is to figure out exactly how it's shared and how that sharing changes with time. It's interesting, in this circuit, it does change with time, the sharing. To figure it out, we're going to start just with the resistor. We're going to start with the resistor because we know the current through the resistor. We know Ohm's law for the resistor, and Ohm's law can tell us the voltage across the resistor in terms of the current through the resistor. So I'm just going to use Ohm's law so that I can write down the voltage in the resistor. I'm going to use a lowercase v. I'm going to put a subscript resistor on it, or R on it this time, because it's, in this case, going to be different for the capacitor. The voltage is going to be different for the capacitor. And all I've got to do is multiply this current, this I naught, by the resistance to get the voltage. But also I could write it in terms of the EMF that's supplied by the battery. And so the expression for the EMF, for the voltage across the resistor as a function of time is this little expression here. It has exactly the same time dependence of the current because the voltage is proportional to the current. The proportionality constant here is just the fact that at time zero, the entire voltage of the battery is across the resistor and none of it is across the capacitor. So this is the time dependence of the voltage across the resistor. Again, it has this exponential form with a negative exponent, indicating that this voltage will start out at a maximum, the voltage from the battery, and then drop off as a function of time, and eventually become zero when the time is much greater than the time constant. What's the voltage across the resistor? Well, let's write that down. Again, a lowercase v because time-dependent voltage. Put T in parentheses because I want to stress that it's a time-dependent voltage. The voltage across the resistor, the capacitor, according to Kirchhoff's voltage rule, is the voltage that's provided by the battery downstairs here, less the voltage that I'm using up on the resistor over here. So it's epsilon, or the EMF, that's the battery provided by the voltage. That's the voltage provided by the battery, less the voltage across the resistor, and that's epsilon e to the minus t over tau. And so this is the voltage across the capacitor. This is quite interesting because you see here, if you think about the moment you close the switch, all the voltage is across the resistor, and actually none is across the capacitor. When you close the switch, this exponential is e to the minus 0 in both cases. E to the minus 0 is 1. So this equation for the voltage across the resistor just becomes the battery's EMF. This equation for the voltage across the capacitor becomes epsilon minus epsilon, which is 0. And so we see that these equations lead to the fact that at time 0, there's no voltage across the capacitor. It's all across the resistor. If we waited a long time, on the other hand, if we waited at a time much greater than tau, the time constant of the circuit, then the exponential will be e to the minus large number over here on the right, e to the minus large number over here on the left. E to the minus a large number is a very small number, close to 0. And so in that case, the voltage across the resistor goes to 0. The voltage across the capacitor goes to the battery EMF, goes to epsilon here. And so those are the two extremes. Between the extremes of the moment you shut the switch and times that are much greater than the time constant, both the capacitor and the resistor have a portion, a share of the voltage, and the portion of the share of the voltage is determined by this pair of equations here. One last thing I wanted to note is that in this circuit, we have an initial current in the circuit, and we called that initial current, we called it I0. And we have a final charge on the capacitor. And we might call that Q0. And we can write the initial current in the circuit and the final charge on the capacitor in terms of the components of the circuit, the capacitors, capacitance, resistors, resistance, batteries, EMF. And so let me just end up by writing that down. So for the initial current in the circuit, at that moment, the circuit is really as if the entire EMF of the battery is across the resistor. So we know the EMF across the resistor is the battery's EMF. We know the resistance of the resistor is R, and that determines the initial current. It's just epsilon over R. It doesn't involve the capacitance, this equation for the initial current. On the other hand, for the capacitance and the charge on the capacitance at late times, at times much longer than the time constant, here we can use the master equation for the capacitance, C equals Q over V. Just rearrange that, and Q, the charge on the capacitor, is C times the voltage across the capacitor at large times, which is the battery's EMF again. So this equation now, which applies at large times to the circuit, this equation just involves the capacitance and the battery and doesn't involve the resistance. And so these two equations tell us the currents and the charges at the first moment we establish the circuit and at times after the circuit has fully charged up the capacitor. And we've explored this problem of the charging circuit for the capacitor using Kirchoffs rules. Previously, we'd used Kirchoffs rules for just circuits involving resistors and batteries. Now here we're using Kirchoffs rules for circuits involving resistors, capacitors, and batteries. In this case, unlike the previous case, we've got a time-varying current rather than a steady current, but you can still apply Kirchoffs rules to the current in the circuit and the voltage across the elements of the circuit.